Good afternoon, everyone, and welcome to the Wireless Distinguished Speaker Series. Today, we are honored and delighted to have Professor Danijela Cabric from UCLA as our distinguished speaker. Dr. Cabric received her master's from UCLA and her PhD from UC Berkeley in 2007, both in electrical engineering. She's currently leading Cognitive Reconfigurable Embedded Systems Lab at UCLA, and the current focus of her group is on novel radio architecture, signal processing, machine learning and communication systems, 5G, massive MIMO, and IoT systems. Dr. Cabric is involved in 3 large multi-university centers, including SRC JUMP, Terahertz Com Center, and NSF Spectrum X. Professor Cabric has won many awards. Just to name a few, she was a recipient of the Samueli Fellowship, the Okawa Fellowship Research Grant, Hellman Fellowship, NSF Career Award, Qualcomm Fellowship, and she's also an IEEE Fellow. Dr. Cabric, thanks so much for accepting our invitation. And we are so excited that you're here. We wish that we could host you in person at Princeton. The weather is not so great today. It's a bit windy, but our campus is beautiful. Please take it away.
Thank you so much, Yasemin, for inviting me. Thank you all for attending on a late Friday afternoon. I hope I'll make your time worthwhile. Today, I will be talking about my research on millimeter wave communications and some directions that we're taking to enable kind of beyond cellular. 5G, in my mind, is what currently 5G cellular communications are aiming to improve. And I'll focus on latency in communications as well as massive connectivity. As Yasemin pointed out in the introduction, my lab covers actually several projects that are organized in 3 research trusts. And today I will tell you more about the millimeter wave communication and these 2 projects that are applying machine learning for beam alignment and exploiting new array architectures in millimeter wave. You're welcome actually to, at our website, we have more details. In the interest of time, I won't discuss the others. So as we all know, the demand for wireless connectivity is increasing, in particular for data rate, as well as for the number of connecting devices, meaning machines, sensors, robots, which are kind of broadly defined as Internet of Things. And spectrum has been a bottleneck for a long time, but now with this explosive demand, there is definitely a need to move to higher frequencies, and millimeter wave is the first frontier that has been explored, even actually before 5G. This was 60 gigahertz band for Wi-Fi connectivity, 802.11ad and AY. And recently, in 2016, there was opening of additional band at above 60 gigahertz for unlicensed as well as license use, 28 and 37 gigahertz. And that's where effectively 5G is trying to improve the data rate for enhanced mobile broadband access. Now, when we look at kind of the performance metrics of both 5G and 6G, we notice that the data rate is just one of them. And the light gray is the 5G, and the boundary of light blue is actually 6G. So what we notice is that peak data rate demand will need to increase even further, but we also have these reliability, connection density, and air latency, which are actually the most challenging requirements that 6G will need to meet. So that's one of the main reasons why lots of people in the wireless community are focusing on millimeter wave, and Yasemin and other researchers are also looking at higher, above kind of this band that I'm looking at, looking into terahertz to enable these technologies. So now, one of the first problems for anyone working at these higher frequencies is to understand the path loss or kind of propagation, and what are the distances that we're able to accomplish. So if we compare from the kind of distance to path loss, sub-6, which is 2 gigahertz where cellular used to operate, and this is just 28, we noticed that at 200-meter distance, there is about 40 dB loss. This is the measurement from New York City. And going back to kind of Friis equation that kind of gives us the guidance on what is the received signal level that we can expect, we quickly realized that this loss has to be compensated with the antenna gains. So this is kind of one of the key differentiator for millimeter wave communication systems, that if they want to operate over a long distance, they will have to provide high beamforming gain that is usually achieved with this large antenna arrays. And the benefit of antenna arrays is to provide the gain, like here. But now if we look at actually the propagation, we notice also that the gain is directive, meaning that the energy is actually focused in a particular direction. And the goal is really to get it in the direction of the mobile. So now, how many antennas are we talking about? Well, there is actually lots of details that for 5G has been already calculated. And in addition to increasing the bandwidth and increasing the number of antennas, we realized that both base station and the mobiles will have to increase their array sizes. And that will increase both power and cost, as well as other kind of physical layer design and network layer design challenges that I will briefly outline. So as we kind of look at now this beam-based communication or directional communication at millimeter wave, we realized that the network topology is now much more sensitive, if you like, to direction on pointing directions of these beams or misalignment. So lots of physical layer as well as network layer algorithms are now revolving around beam management. In addition to beam alignment, we also are looking at supporting multi-beam connectivity for spatial multiplexing. And that again increases the complexity of these antenna array architectures that we're putting. Today, I will focus on this problem of kind of alignment or misalignment, and what does that mean for the mobile, especially for the initial access, where we need to kind of blindly find these directions as well as tracking. And for that, there is also a question of how costly can the radio can be in terms of both hardware cost as well as power. So that brings me to the question of our antenna array architectures. And traditionally in like sub-6, we have kind of mostly assumed this digital array where you can dedicate for every antenna a single RF chain, and then lots of processing can be done using digital signal processing, and therefore the algorithmic framework for doing channel estimation in this MIMO was not so critical aspect, although still challenging. But in millimeter wave, we realized the number of antennas will increase, and therefore these are architectures that are reducing the number of radio components per antenna are becoming more practical. So we have these hybrid arrays, or even the simplest one would be just using one digitizer, both on analog and both on transmitter and receiver side to do that. So that's kind of the trend in terms of cost. If you look at from analog, which is a single RF, one spatial stream and just one front end, going all the way to digital, there is this increase. However, as we'll learn, the capabilities to achieve these beam alignment fast kind of are having this trend that analog are actually going to require a lot more overhead. And that's kind of what we want to resolve and try to find the architectures that can kind of strike the balance and enable both low complexity as well as low training overhead. In the second part of the talk, I would also like to touch upon another segment of beyond 5G, which is looking into connectivity of IoT devices. So within current 5G, there are two segments. One is focusing, these are the axes of reliability and latency, kind of combining the two because they are related. And this one is the number of devices. So 5G currently has solutions for high reliability, but relatively low number of devices, as well as very large number of devices, but then in terms of latency, it's not a critical parameter in reliability. So we envisioned that, and there are actually lots of applications from industrial automation, vehicular kind of autonomous cars, virtual reality, that will actually require larger number of devices, as well as to improve the reliability, as well as data rate. So there is this table again, kind of summarizes, this is currently 5G, and this is the new segment that is increasing the data rate, lower latency, and also connection density than these two IoT segments. And millimeter wave will be actually one of the technologies that, or like we'll try to solve this in millimeter wave band. So now, why is millimeter wave band challenging for IoT connectivity? Well, if you look at the solutions for existing, they are in below 6 gigahertz, and this is kind of, there are no antenna arrays, everything, all the resources are effectively scheduled using OFDMA, which is very suitable for flexibly using, and that's kind of what 5G NR is beneficial for, that you can really schedule users adaptively. However, as soon as you move to millimeter wave, you start adding these antenna arrays and directionality, and then you run into a problem of scheduling, because you have to kind of change these beams, or kind of when you schedule the resources, you also have to do this beam alignment. And moving into higher frequencies, the problem becomes even more challenging, because the beams are becoming narrower, and the number of devices that you can schedule is reducing. Now, if you remember, we have lots of bandwidth, but exploiting both large bandwidth with this directional communication for IoT devices that cannot be extremely wide bandwidth and have a large number of antennas is, again, also practical challenge. So in this talk, this is kind of set up for my three parts of my talk. First, we will look at this latency problem of beam alignment and propose machine learning assisted approach that will achieve a fast connection, but it's going to use this phased antenna array architecture that I introduced in the beginning. And then in the second part of the talk, I'm going to introduce a new array architecture that is exploiting true time delays kind of applied at the antennas to realize a new beam forming technology, which we'll call rainbow beam, and we'll show how this new architecture can support very fast, like a single OFDM symbol based connectivity in terms of beam training. And then in the third part, I will then switch to this IoT problem where we're going to extend these rainbow beam approach through two time delay to develop a medium access technique that will allow us to connect very large number of devices over a wide bandwidth, but without requirement for beam alignment, as well as very low light scheduling, if you like, or there basically no scheduling to achieve the low latency communication. So let's start. So first, I hope it's very intuitive to understand the beam alignment problem, which essentially means that you realize that these beams need to be pointed in the right direction so that we realize these beam forming gains. So how can both base station and mobile find this? And again, if we're limited to a reduced search, in some cases only one beam at a time, then you have to kind of come up with intelligent algorithms. So existing approaches either use hierarchical sounding or some new beam patterns that can accelerate this. And from the theoretical point of view, actually using something, the beams that look like red and blue here, which don't really look like a directional beam, turn out to be very promising because the millimeter wave channels exhibit sparsity, and these pseudo-random sounding actually is good for finding sparse signals in general. So this is kind of where the state of the art from signal processing has found that these approaches can reduce the search with n antennas to logarithmic log n number of probings. So this is actually where we started our research, and we wanted to demonstrate how well this compressive search would work. To realize these beams is actually very easy. The phases of your antennas just need to have a limited number of degrees like it's here. Now, one problem with beam alignment in general, especially initially when you're trying to connect to the base station in a low signal to noise ratio, you have to do it through some sort of non-coherent like energy or receive signal strength measurements. So we have kind of looked at these kind of phaseless or energy-based measurements to these pseudo-random beams. And turns out that these measurements based on different probing indexes or different beams exhibit a fingerprint, or basically a particular shape for a particular angle of arrival. So here I have example of angle of minus 30 degree, which is the black line. So even though it doesn't really tell us that the angle is minus 30, these measurements have this shape that can be used through a suite of compressive sensing algorithms using phase retrieval to identify this angle. Similarly, the angle 0 has a different fingerprint. So this all sounds very promising. The only thing that became challenging is when we started implementing, we realized that what we have predicted for these fingerprints and what we have actually measured, and I'll show you later on our test bed, we realized a huge mismatch. And where does this mismatch come from? Well, antenna arrays that we're using are not perfect. And in general, the more antennas you have, you will run into offsets in these phases that we're programming, even at the quantized level. Also, the way the layout of the phase shifters with respect to antennas is done, as well as some defects or snow and others. So effectively in practice, it's very hard to have a perfect match between theory and measurements, or basically the beams. And turns out these compressive techniques are highly sensitive. So what was our idea? Well, we know that, and this is actually even for this Wi-Fi at 11 AD, that this directional beam probing that basically works by sweeping a very nice beam and finding these directions is robust to hardware impairments. The only problem is that the overhead, the number of probings, is proportional to the number of antennas, and that's slow. Now, the compressive way, which are these pseudo-random beams, as I said, scales logarithmically with number of antennas, but now it's sensitive to the array impairments. So our approach actually combines these compressive sensing measurements, but uses machine learning to correct for sensitivity to array impairments. So we have developed this algorithm called MMRapid that is effectively trying to improve compressive sensing in the presence of array impairments. So we treat it as a kind of a classification problem that takes as an input a set of measurements through M pseudo-random probing beams, and the network is predicting what is the best direction, or what is this directional beam that we should apply, because that's our end goal. We want to connect. Now, if you remember, the hardware impairments are actually corrected by this neural network, but we have to train it. So the training is done by actually using two sets of measurements, and it's done online, meaning every mobile can train itself in the field using the DFT beams, the nice directional beams, and pseudo-random beams, so that it can learn how to associate basically the PN beams with the right labels or right directions. And then in the operation, we switch only to PN beams. So this is how it works. This is our online training or array self-calibration. Basically, the mobile would initially, this is during the training, do the probing, and then it would also do the probing with a pseudo-random beam. So these directional beams are giving labels for our neural network, and the pseudorandom beams are giving us features. So we have implemented this or experimentally verified using this millimeter wave testbed at 60 gigahertz. This is actually Facebook Telegraph. This is their actually it's a product now. It uses 802.11ad protocol over 2 gigahertz of bandwidth. And it has 36 times 8 planar arrays. And actually we were able to program all these beam patterns and take measurements to support our algorithm design. So first thing, you have seen this already. We have seen that these pseudorandom beams have mismatch between the theory and model. However, these directional beams, I call them DFT beams, are actually they're calibrated. Actually, Facebook calibrated their array, but they calibrated it only for these directional beams. They didn't calibrate for all possible beams, and that might not be even practical. And therefore, we use these DFT beams as our ground truth or labels because they can tell us very good measurements in the direction of our IO. So the result was actually very exciting. We have shown that the number of measurements can be significantly improved. So this is number of measurements that we need to take in order to achieve a certain beam alignment. Sorry, there are lots of algorithms here. The green one is what we have proposed. And we see that in the line of sight network with up to 5 measurements, and remember we have 36 element antenna array, we can achieve below 1 dB loss, meaning that the misalignment is very, very small. And the comparison is actually compressive sensing approaches because that's our benchmark for pseudorandom beams. And we see because of hardware impairments, we have this degradation. We have also analyzed for larger arrays what would be the performance improvement. And this is kind of our scaling logarithmic with n. But we noticed that our neural network actually also has this gain even without hardware impairments. And then if you put hardware impairments like we have here, which are realistic ones, we see that the compressive sensing is actually not the square, but the triangle. And therefore, this blue curve might even shift upwards if we don't correct for it. So this is line of sight channel. Our extension was, okay, looking into now channels that have not just one strong path, but they also have these non-line of sight paths. And if you remember, because we're doing these non-compressive measurements, there is actually a kind of interference between these paths. So what we have done is first we have identified the problem via simulation. So we have generated this synthetic channel that has the strong line of sight and then L paths, which are decaying with this exponent alpha. And the stronger the, sorry, because it's minus, we have that line of sight is basically alpha to the 3, which is kind of our line of sight, where we get very good accuracy with smaller number of measurements, while for the heavily non-line of sight, we actually have very poor performance in terms of accuracy versus number of measurements. And again, the insight is partially because of these phaseless measurements and partially because of the pseudorandom approach. So this is kind of when you decompose that, you end up with your desired paths, which are L of them, but you also have these, so information is basically due to this interference, corrupted to identify these directions of our components, main directions. So we have actually explored now, there are two kind of ways of attacking this: design a better algorithm or try to improve on your beams. So we have done both. First, we have added additional kind of beams into our code books. So remember my pseudorandom beams, but we also added these multi-finger beams, which were actually inspired by prior work that showed that their directionality helps, as well as this wider directional beam, which is the green one. And why do we have these three? Well, if you have actually phase antenna array, you're limited to code books that can only change the phase. You're not allowed to change the magnitude. And these are our candidates in addition to that DFT beam that I used initially. We have also measured our array responses for different codebooks. And again, this is our DFT beam. And then this other one is the more directional, the better calibration. But again, we have these pseudo-random and subarray mismatches, which again motivated machine learning approaches to compensate for beam deviation. The other thing that we have done is also with these new types of beams, we studied correlation between the measurements. And here is the correlation between pseudo-random beams. These are the wider beams and the subarray or multi-finger beams. And we have noticed that there is actually correlation between measurements, which inspired us to now look at convolutional neural networks to exploit this correlation, in particular for these more correlated measurements. Again, we have conducting experiment. This was actually during pandemic. So we were inside of indoor. The first experiment was outdoor. And here we were able to do kind of create multipath channels using these reflectors and line of sight blockers. We kept the distance about the same as in the first experiment. We slightly widened the beam on the transmitter side to basically illuminate the space and get more reflections. In addition to simulations, we have done also experiments. We have done simulations just so that we have some kind of comparison with what the model tells us versus what we get in the experiments. And the assumptions about beams that we use are the same. If you remember, the channels that we generated in the simulation were kind of synthetic in a sense that we changed this alpha, how fast the non-line of sight decays, versus in the experiment, we got what the environment gave us. So here is the first kind of result, and this one is showing us the comparison in terms of algorithms. So if you remember, our first architecture was like fully connected neural network, and then we switched to the convolutional neural network. And we also compared it with the matching pursuit approach. So basically, this is our matching pursuit, which again, we expected is not going to perform well. And we got slight improvement from the CNN in all cases. I mean, here it's the scale, but CNN actually gave us the improvement in all three scenarios. This is what type of beams we use: pseudo-random beams, pseudo-randoms with multi-finger, or multi-finger beams. Now, with respect to which, if you remember, there were more than just pseudo-random beams, we have explored using only multi-finger beams, using combination of pseudo-random and multi-finger beams, using pseudo-random beams alone, and pseudo-random with wider beams. So the results are, I mean, these are actually the experimental data in both cases. And given the limited number of measurements, a couple of thousands, I mean, the curves are not perfectly smooth, but they're still showing trend that the blue and actually purple ones are effectively, these are just different channels in terms of how much line of sight, non-line of sight we have, are giving us better performance. So basically, the subarray or multi-finger beams are actually helpful because they have some directionality versus just pseudo-random beams only. This is again in terms of how much savings we get in terms of combining convolutional neural network with these hybrid beams, and in all cases, based on how much non-line of sight we have, the number of measurements is significantly reduced compared to just using, let's say, compressive sensing or these pseudo-random beams alone. We're currently exploring the beam tracking, and actually this approach naturally extends to tracking. The idea is again to use the pseudo-random beams to quickly predict what is the best beam forming direction and kind of use a little bit of a memory in the system to even predict what are the future beam forming directions. So this is just a little bit more detail. I don't have any experimental results, but we have developed the algorithm that exploits now the LSTMs in our prediction to find not only the current best beam, but also saves us time in the future so that we can accelerate beam tracking. So this is, again, non-line of sight channels where we have now traces of multipath and random trajectories. For example, here is how the signal changes in azimuth and elevation as the person moves. And we have shown that the proposed architecture is able to predict both azimuth and elevation with a true angle. Okay, so this was our kind of machine learning assisted beam training and combining it with different beam designs. And the results are showing that we can significantly save on the overhead in beam training. However, while we were kind of pursuing this approach, the limitation was really, phase antenna array and single beam at a time. So this is kind of where our new research direction started with this new array architecture that, by the way, is still analog. What I mean by that, if you think about, and I'll contrast that in a second, this true time delay architecture is, before I was assuming that I can per antenna change phases. Now it has these delay elements per antenna. It's still single RF chain. So before, when I was talking, I was basically pointing one beam, which this architecture can do as well. However, this true time delay has capability that by changing the delays, you can achieve the following. You can now extend the bandwidth of your system. What that means is that if you didn't have the delays, this beam would actually become frequency dependent, and it would exhibit what we call squint. It wouldn't be actually same for these two frequencies. So the small correction, these D are corrections in picoseconds, are making a wideband signal create a perfect beam. So this is actually what true time delays arrays were known for. It was just a question of, can we really implement them at a cost? And today we can. Now, what we have actually explored is this new mode, which is what you actually use for, people actually didn't think of this mode because they didn't quite see its benefit in communications. And the idea is to disperse, to basically create with this one RF chain, two beams, and basically point two different frequencies into two different directions. And how do we achieve that is basically, I'm just gonna show you now empirical result, which is if you increase the delays per antenna, you get this dispersive mode. Now we will derive how do we come up with this result in a moment. But what's nice about it, this mode is actually what we will exploit to accelerate the beam training. And we can also achieve the use phase shifters to do the beam steering like we did in phase antenna array and have control over different directions. So how do we do this frequency to angle mapping for the dispersive mode? Well, we have derived how in a true time delay, the beam steering vector depends on these delays. And turns out that these phases, before it was only a phase, but now I have the delay, can actually create for different frequencies equivalent phase. And this equivalent phase maps into our steering angle based on this inverse kind of beam pattern equation. So effectively, steering direction of the mth subcarrier is mapped to a particular angle. Okay, so we can also do this, and we have explored this in the so-called 3D beamforming in practice, or maybe many papers actually use this planar arrays, which effectively requires both elevation and azimuth beamforming. So how does true time delay work in that case? Well, you have also delay elements per antenna on that plane, and then you can control both azimuth and elevation delays independently, and then the final combiner is computed by, you'll see, effectively adding the delays in elevation. These two are added to create the final beam pattern. So again, we have developed mathematically these frequency to angle mapping. Now, because we have two angles, we have azimuth and elevation, the frequencies are kind of mapped in these patterns. And based on the delays that we put, delta tau in elevation and delta tau in azimuth, we can realize different patterns. So what I'm showing here is actually something that's even more interesting. and that is by controlling how much delay you put per between the elements. You can, the yellows are showing where the beams are pointing. So yellow means that you have a gain, and this is like a 3 dB gain in that direction. Blue, there is no gain. So we see that this one can steer all azimuth vertically only partial angle, and that will depend on how we set these delays. We can track or scan region, or even smaller region in our 3D space. What you notice here is that the delays spacings become smaller. In order to arrive at the full spherical coverage, you actually need to achieve these delay spacing that is proportional to the 1 over bandwidth, and actually increase it significantly to realize this beam pattern. So now I already revealed parts of my design, which is if you notice, there is 1 over beam bandwidth that you are operating over that you need to set to create these patterns. So now let's now go into a little bit deeper design for beam training using in these analog TTD arrays. And I will assume that this is again cellular system where base station is using even digital array. Why digital? Because this is one antenna, one RF chain per antenna, because we can maybe afford the cost and power. But on the mobile side, I'm putting these through time delay, and therefore I can only measure one stream at a time. So we are assuming OFDM system that uses bandwidth BW and has total number of subcarriers. And the base station is going to use pilots to load certain number of subcarriers to help estimate the channel. And effectively, we're estimating just the angles in this channel. The channel is frequency dependent, frequency selective, but the key is to do the beam alignment and find these angles between, like plotted here. So the received signal is just an OFDM symbol. And the goal is to design these W, which is going to depend on how we steer the through time delays in our array. So how do we do that? Now, if you remember, our goal is to create this scan of angles, right? We had that equation that showed us how the angles are scanned. And if I want for these angles to scan from -π/2 to π/2, basically I want for this psi, which is, remember, there was a psi to alpha angle. We want for this difference between the first subcarrier, which is this one, and the last one to span 2 pi, which effectively tells us that the phases, this delay spacing, should be inversely proportional to the distance between the two, which is that 1 over bandwidth. So our single shot codebook is basically telling us that with spacing of 1 over bandwidth, linear spacing between, uniform spacing between the antennas in terms of delay, we get this full scan. So I hope by now your intuition has developed that these beams are, and colors are here used to represent different frequencies. This is 400 megahertz of bandwidth, and I have 16 elements through time delay, only one RF chain, and I've set now my delays to be 1 over bandwidth of 400 megahertz, and I'm creating now these rainbow beams. And effectively, each subcarrier is now, there is a map or like a lookup table of these directions. I can use the phase shifters. These are phase shifters are all 0 versus changing them based on this pattern to now switch and use this subcarrier to point into this direction. So we can do the rotation. One problem with actually our approach for dispersive beams is that indeed the delay that you need to physically realize is becoming a bottleneck. So if you have NR element antenna array, then the last antenna in your array will require a delay of NR -1 over bandwidth, which becomes tens of nanoseconds, and hardware-wise, that might be challenging. So what happens then is that we cannot really span the entire 2 pi. We might be able to span only a segment, which is okay. It means that our coverage might be limited. But since we have phase shifters, we can do these rotations And therefore, I can create two sets of these rainbow beams to cover the entire angle. So my training might not be with a single OFDM symbol. I would have to do it with two. That's one if you have a delay constraint. Now, with this rotation, we realized that actually the true time delay arrays can also achieve the diversity, meaning that I can use more than one subcarrier to be mapped to a given angle, even if I don't have the delay constraint. So there is a 2 pi coverage, but I can, through rotation, map more than one frequency and avoid fading over using only one subcarrier. So this is how the rainbow beams look like with that constraint. This is now reducing it by half. Partial scan, but we can do the rotations. So we have, as I said, demonstrated, this is in collaboration with the group from Washington State University, where they have these true time delay chip with 16 element antenna. And these are these beams that are, that we have basically predicted that we can point particular frequency in a particular direction using our true time delay approach. And this is that kind of scan angle versus frequency where we see that relationship between mapping which frequency points into which direction. In terms of how do we now use this for beam training? Well, if you remember, the base station loads the subcarriers, and the idea is that we want to use a minimal number of subcarriers to do the scan, and we want to load them with a power. So here is one option, which is uniform loading, and here is kind of extension to 3GPP that you can also use resource blocks. And the course algorithm, this is the first algorithm that we have developed, is using frequency measurement, right? Every subcarrier would have a certain signal strength, and the one that has the strongest signal strength is basically the one that is receiving the signal from the desired direction. So that's very simple. We have actually extended this to quite, high resolution algorithms with some more advanced code books. But in any case, just as a proof of concept, we have studied how well this performs and compared it also with phase antenna arrays. So this is kind of a typical 5G setting at 28 gigahertz with 2048 subcarriers and using only a subset for pilots in terms of resource blocks. And the channel signal to noise ratio is -30. That's kind of maybe 200 or more distance, and in different channels that are typically used for millimeter wave. And here is the result that shows with this rainbow beam style training, getting into like -20 pre-beam forming SNR, you can actually achieve with a single OFDM pilot almost perfect alignment. There is -2 dB loss, and then you're quickly getting to a perfect alignment. And here is kind of exploration, how many subcarriers or resource blocks to use. And if you notice, the blue, which is less, is good if you're in low signal to noise ratio, because you can load more power in these subcarriers, right? This is kind of the subcarrier loading. And then once you are in good signal to noise ratio, then it's actually better to use more subcarriers because that improves your resolution. This is similar, this is post-training gain. This is how much error in the angle we achieve as we scale the number of antennas. And again, this is showing advancement of this technique to improve the resolution by using diversity, or kind of adding more subcarriers that scan direction. So this is our subcarrier mapping, but now we are adding redundancy. The blue subcarrier is now, all blue subcarriers are mapped into a particular direction. And how do we do that? Well, with the repetition R, we need to extend that delay. And then we also need to do the phase alignment if we want to do the rotation. So now you might wonder, I just told you that increasing the delay is problematic. So how are you going to achieve this diversity if you are limited by the delay? So this is where we started exploring new true time delay array architecture. So this is actually more detailed one that I used to show how we change these delays. And here are the phases. So this is kind of a zoomed in version. And this is what we call analog TTD array architecture. Now, if you have a delay bottleneck, actually, then it is more beneficial to use this hybrid. So I showed you hybrid for phased antenna array, but there is also hybrid for true time delay. So effectively splitting antennas into groups, and then each group now has a smaller delay range, and then the effective delay is by combining a digital delay, which can actually realize you don't have any limitation because that's a digital implementation. So we have shown that through this diversity, we can exploit more bandwidth, which we already have in millimeter wave, as well as improve the angle of arrival estimation accuracy. So this is the comparison of analog, hybrid, and digital. And analog, we had some diversity, but again, we were limited by this maximum constraint on the delay. And with hybrid, we see that we can actually go into 16 level diversity of 16. And obviously our benchmark was the digital, where we don't have any constraint on the diversity, and we can use maximum likelihood type of estimator. So this is kind of the SNR. I believe that this is SNR of -10 dB. One thing that obviously for our hardware people, this was very important, but also some people were skeptical about controlling these delays and how fine do we need to do that and how sensitive this approach is. So we actually did a study on how much our accuracy of the estimation or alignment would be degraded if we have errors in the phase shifters as well as in the delays. And turns out that obviously hybrid has relaxed requirements on the delay, and therefore it is performing better, and the sensitivity is actually kind of close to 200 picoseconds. And our collaborators actually have state of the art, which I think is like 5 picosecond in accuracy. So these numbers are actually not something to worry about. Okay, so this was our kind of new approach in using true time delays for beam training. Obviously, when you go to communication, you would have to create like one beam, similar to what I had before. But then we started thinking, okay, so these new rainbow beam, are they good for communication? And that's kind of where this idea of using them for communication in massive IoT networks came about. So let me tell you what the insight is. So the problem is that in millimeter wave, we have lots of spectrum, right? There is huge bandwidth. And we would like to use this bandwidth to serve a very large number of devices. Now, the cost of the radio increases with bandwidth, right? And indeed, these devices do not require huge bandwidth. They don't need 2 gigahertz of bandwidth, meaning 2 gigabits per second. They might need the order of tens of megabits or even a megabit per second. And therefore, I would like to have their bandwidth small. So now the question is, how can I divide this huge bandwidth between these devices? Well, that's kind of what the OFDMA does for us. But at the same time, we also need to do a beamforming, which requires us that the base station has this beamforming gain. So it turns out that actually these rainbow beams are doing beamforming and OFDMA in one shot. So what they're effectively doing is they are illuminating a subset of IoT devices or UEs with a set of frequencies. So for example, these blue frequencies are also spatially mapped to all the users that are in this angular sector. And therefore, you are kind of dividing frequency based on their location. So that's the first one. The second one is that we don't even have to have multiple antennas on these IoT devices because we will leverage the beamforming gain from the IoT gateway. And then we're already aligned because we are aligned both in frequency and angle. So there is no that search for frequencies. Now, the remaining part will be when I bring density. I have here a very small number of devices, but there is a problem in access that we have to solve if we really want to make this massive. So this is how we set up our rainbow link. So this is, again, you have seen my true time delay array that's going to be put on the base station or IoT. And I'm going to use this exactly same rainbow beam, but now I'm going to populate the space with lots of IoTs. These little crosses here are IoT devices in a 400 meter, let's say, radius. So these IoT devices, now I'm just zooming in one, are actually narrowband, as we said, and the bandwidth is actually equal to how many subcarriers is this base station using, meaning its bandwidth, over the number of antennas it has. So here is my, and that's kind of where I also can control what is the bandwidth of the IoTs. And all these subcarriers are actually getting the beam forming gain. So there are two procedures that we need to develop. And one is how does this IoT synchronize, or basically synchronize both in frequency and time, and connect through these best subcarriers. And the other one is, what if I have more than one IoT, like I have in this segment more than one IoT, then they'll have to contend. So we have developed this, and what's new? I mean, people have done the contention-based algorithms, medium access protocols. What we have done is we have combined these beam alignment-free and grant-free access by effectively doing only a two-step random access. So as I said, nothing to do with beam alignment. We don't even need that. But the contention is now, not resolved, meaning in fourth step, you would have to have request to send and get clear to send. Well, here we don't have that. What we have is the base station is basically just broadcasting the synchronization sequences. And then the mobile is receiving them, or the IoT is receiving them, and then contending, meaning that whoever is synchronized and has a packet to send will collide effectively. So that's that synchronization contention protocol. And the goal is to really get the low latency, even under these high density. So first part was we studied this rainbow beam style of synchronizing, whether the devices that are operating over a very narrow band, right? I'm using 2048 subcarriers, but my IoTs have only between 8 and 32, and they are, as I said, in 400 meter distance. What is the probability that they're going to sync up? So this probability of synchronization is actually going to map into a latency, because if I cannot synchronize, I have to wait. And that's actually what, in order to really understand the latency part, you have to study probability of synchronizing in terms of time. So this is in sync probability. And now the question is, if I want to target, let's say, below 1 millisecond latency, which is here, what is the probability that I'll synchronize? So what we have compared is actually with some benchmarks, which are using phase antenna array approach, meaning that they'll have to sweep or illuminate. So the blue one, let's say 4 RF chain, and then you have more RF chains to increase coverage spatially, versus through time delay and fully digital. And we see that our in-sync probability is high, and we can be far below 1 millisecond with 10 to the minus 6. So that's a reliability requirement. So this is just the first part. The devices can now synchronize through these rainbow beams because they have enough beam forming gain, and they can actually use their narrowband receivers to do so. Now, the second part is the contention. For that, we have decided to use a grant-free access, and for collisions, we are exploiting the repetition, basically, repetition coding strategy. So what that means is that if I have IoTs or users that are within the same rainbow beam, they still have a set of subcarriers. Basically, these are the subcarriers, for example, 8 subcarriers, to choose where to send their data to. So if they choose randomly, right, that's the random, they'll all repeat 3 times, but if they repeat in a different way, then the probability of collision will reduce. So here we have an example where I have at least one successful packet from each of these IoTs. So hopefully that intuition is clear. We have studied that analytically. We have asked ourselves, what if I have 20, 30, or let's say 40 IoTs contending in the same rainbow beam slice? How much do I need to repeat to get the minimum packet loss rate? So it turns out that that's around 5 to 3 repetitions is actually optimal, but we have that number actually, this analytical formula that tells us how much do they need to repeat. And remember, repetition will also reduce the rate of their communication. So with that, we have then studied our total latency budget, accounting for contention and then synchronization, because as I claimed, we wanted to show that this scheme can achieve ultra low latency, which is below 1 millisecond. That's how people are defining it, with, let's say, 10 to the minus 6 probability. So what I'm showing here is a network that has radius, it's a semicircle, 400 meters, and it has almost 1 active user per meter square per second. Okay, so it's pretty dense. And here is our synchronization. That's basically the same, but now we see that in addition to that, we have the contention. And how much contention I get, it's there are 2 options that we have explored. There are many actually flexibility that you have in this design. We have looked at how many subcarriers are grouped in a resource block to increase the data rate. So the purple one has higher data rate because it uses 4 subcarriers per resource block versus yellow one, and therefore has a higher contention and longer latency. But in any case, they're both below 1 millisecond. And this is their total delays, blue and orange. So this is nice because, as I said, the latency is still for dense networks within the margin, and then we also can trade off rate. If you want higher data rate, maybe we have to extend this or use more bandwidth. Again, this is that massive connectivity and rate trade-off. Now scaling the network size, that's another parameter. So if you remember, my first example was almost 1 user per meter second per meter square per second, and this is almost 5 times, so 5 active users. I'm increasing density by 5, and I'm achieving kind of the same latency statistic, and what I'm trading off is actually the rate. Now I have to reduce the rate per user by a factor of 4. And here is kind of another rate. I think there is also lots of study that one can do in terms of what are the trade-offs between the latency and massive connectivity and rate in this setting. But again, this is showing from the sum rate point how much base station can deliver. Grouping less subcarriers, meaning lower data rates, is more beneficial. But it's again application specific. So in conclusion, this for the second part of the talk, this true time delay architecture is really a promising candidate for many millimeter wave related problems, both in this initial access and beam training. As I said, first application was really for data communication to overcome the beam squint and also potentially cancel wideband interference. And our kind of recent work has shown that they have applications beyond cellular network, for example, in this massive IoT connectivity. I just want to end with acknowledging actually the people who have contributed to this. These are my PhD students, and also funding from 2 centers, Com Center and JUMP, their SRC, as well as donation from Facebook. And if you're interested, I know I covered a lot. There are a set of papers on these 3 topics, and I would be happy to answer questions now, but here are the details. Thank you.
Great, wonderful. Thanks so much for this interesting talk. I have so many questions now, but I'll start with one, and then for the audience, please either unmute yourself and ask your question or just leave it in the chat and we go over them. So first question is from sort of the first part of your talk about pseudo-random sort of beam. It seems like there is room for sort of online learning if you're doing pseudo-random combined with sort of a predefined set of directional beams. So you can kind of maybe optimize the shape of your sort of directional beam on the go, depending on the environment. And have you looked into that?
Yeah, that's kind of reinforcement learning approach that we are, I would say I'm writing a proposal about it. I don't have a paper yet, but as you know, you have to sometimes have, I mean, we have some initial results which are using that. I mean, there are actually two approaches. One is, can we actually learn what the best beams are for a given environment and then put that in our, I call them a super code book. Like you have a lot of beams to choose from, and then you have a reinforcement learning agent to kind of pick for you what are the best beams to choose. Yeah, so that's definitely a direction for online learning that is a natural step, I think, for this, right? And I also showed like you can reduce, but the question is, in each environment, the number of beams will vary, right? So you have to decide, you know, is it 5, 6, or 7? You cannot, if you start doing it up front, then you're again not suboptimal.
That makes sense. Yeah, great, thanks. We have in the chat YK Chen asking, have you considered the Doppler shift for beamforming, particularly at millimeter wave range?
No, we have not. I mean, I'm not quite following the Doppler shift for the beamforming. I think that the tracking part will try to cover the mobility. And right now we're looking at kind of pedestrian type of speeds where we think that our the number of measurements for this first approach, right, might still have to reduce, right? Maybe 5 or 6 is again too long. Can we do it with 1 or 2? Yeah.
YK, if you have a follow-up question, you can unmute yourself. I do have one question about your sort of true time delay structure. If you have a mobile user, then you're expecting to see changes in the channel and power across subcarriers. Have you looked into real-time tracking using true time delay?
No, not yet, but I think that tracking is kind of our, I think, natural extension, yeah. Yeah, but I think with this, I mean, you can use a multiple rainbow beams, right? Or you can even with a single rainbow beam. I mean, it's still kind of, we believe that one WebDM symbol is still very short, right? And if you can do things within from one to another, you have a perfect estimate, right, of where the things are. So that kind of gives you tracking.